Fernando Posada from Group Leader for the System Acceptance and User Environment Group at the National Center for Computational Sciences in Oak Ridge National Laboratory. As you may already know, NCCS hosts the Oak Ridge Leadership Computing Facility, which is the house for the Frontier Supercomputing. Right now is the largest supercomputing for open science, so we have to that clarification because the Capitan is now the first one. Anyway, so today I'm going to talk about the experience we have and my team has had in deploying the software for Frontier, particularly using a tool that we call NSP, that stands for NCCS Software Provisioning. But you might be thinking, why another tool? So I would say it's not a tool, it's more like an approach in how to install software. But I want to talk about the software stack complexity of Frontier and why it is necessary to have a way of manage so many environments. And as a context, you may already know that ECP and specifically also IFRS as well, they have dramatically increased the amount of available software to run at scale. Right now, we're managing around 100 applications, but each application has to be compiled for several CPEs, which are vendor-provided software stacks, so private ones that the previous speaker was talking about. And then each application also has to be compiled for the 3 compilers they support. So they have CC, AMD, GCC. Then we have to compile them with or without GPU support, with MPI or not MPI, with OpenMP or not. So as you can imagine, this is growing very quickly into a massive issue. So before NSP, we were having a lot of issues into integrating the vendor-provided software with our software modules. I have to disclose that I've been in the lab for 1 year, so I'm fairly new to Spack. But when I came in, the person that was managing it had only one Spack YML file with around 1,800 lines, so that was impossible to read. It was taking weeks to concretize, and it was that bad that that guy left the lab because I guess he reflected on his decisions in life. He decided to buy a boat, and now he's sailing the ocean. I don't know. He left the lab. So we say, OK, so we have nothing, so we have to rethink this thing. And then we decided to take as a mantra configuration as a code, right? So we wanted to have something that is trackable, reproducible. I already had a lot of experience in using Ansible. I didn't have experience with Spack, but that was the thing that we were using. So I decided to focus our approach in using Spack, leveraging Ansible, Spack, and also using LMOD. So the strategy was basically to instead to having this very large environment, just to split it into smaller pieces. But having many smaller environments means you have a lot of code repetition. So that's where Ansible comes in place. You will see later in the presentation. And then the other was just configuring Spack to create the modules in the way we wanted, not that the Spack is by default used to do them. And then we modified LMOD with LMOD hooks to be able to read the modules that were produced by Spack. So everything was integrated into one product. But NSP is also capable of doing more than that. So this is more or less the workflow in total. So we have a CDCI. So usually if this works automatically, then it will pull the roles, Ansible playbooks and roles from our Git repos. Then it's going to run the Ansible playbooks into the machine. So it's going to configure LMOD. It's going to install the Spack if that's a word. Then it's going to install Miniforge, but we can also install things like CUDA, GCC, and many other things that you have to install manually. You decide to install manually, I have to say, because you couldn't. With the Spack, you could do it, but some things are decided to install manually for reasons. And then there is another step in which you will activate the environment, you will concretize it and install it. Everything is automatic, and more or less that's the idea. So the reason why we have 2 repos is because we have a public repo in which we offer to anybody who wants to use it the roles that we wrote for this. But then we have a private one in which we store the configuration that we use for our system, so Frontier and many others. But we do provide documentation for users so that they can create their own playbooks, even to users if they want to use our installation as an upstream. As I was mentioning before, so NSP has more than Spack, so it has GCC, CUDA, and many other. But I'm going to focus on Spack because I only have 10 minutes, and so I'm going to talk about the Spack role. I will call it a meta layer to Spack. So basically what it does is that it generates the configuration files that you need to create environments. So for example, here, this is the playbook for Frontier. You can see you have a list of environments. The list is longer, but just to show you an example. So you have a name of the environment, and it uses a particular version of Spack. And here, we define that version of Spack in a variable section, right? So then that, when it's run for Ansible, it produces folders for the environments, as you can see here. And each folder will contain the necessary configuration to run the environment. Something went with the environment, you can delete the folder, nothing happened. You can run the playbook again, and everything will be there again, okay? So that's the main idea. Somebody opens the file, and by mistake, they edit them, change something, you run the playbook again, everything is going to be restored. That is more or less the idea of using Ansible. But how are those files then created? Well, those files are created using what we call, I think this is something that Spack has, manifest in variables. So that will be the CRAPE applications in their corresponding version for a given CPE release. And then we will use these templates that are the Ansible templates that will have the placeholder for the version. And then we run the playbooks. The rendered product will be the configuration file that you need for a particular environment. Since you already saw this in this structure, they are completely independent. So you're not having cross-compiling issues, or when you're concretizing some compilers mixed with the other one, they are completely separated. The only thing that actually joins them is the place where you install the modules. And there is the other problem. The problem that we had with Spack, that was that the modules were created sometimes with random paths. And random comes for the hash that was sometimes added to the paths. So the reason why then, particularly because we have to use Rockem, and Rockem is not allowed to be a virtual package, so you couldn't include it into the hierarchy. We decided to create our own hierarchy, basically leveraging what we call the projections. What are the projections in Spack? So basically, this part that is here in red is where we put our hierarchy, and basically has three components, which is the compiler, MPI, and GPU bin. Compiler with less weight, and then you will have the most prominent will be, I think, is MPI, as you can see here, then the GPU part, and then the compiler, each one with the corresponding versions. So just as a recap that I was saying, so you will have, in the previous configuration, you will have something like this. So MPICH will, for some reason, have hashes in there. But now with the new configuration, you have something more cleaner like this. So you have, if you were to have something with GPU and MPI support, you will have this path here. So first MPI, then the GPU part, then the compiler part. You see everything is represented. Everything is kind of predictable, right? And in that way, or I want to explain before how we did it in Spack. So this is a Spack configuration file. Basically, we put projections for every single case. So in the first one, you will have the GPU plus MPI, then only GPU, only MPI, and the default case where you have no GPU and no MPI. All right. So just a summary, the way it works from the Spack role point of view, then you will have the Ansible playbook. You will run Ansible. It will produce the environment. Then we will have a tool called Spacktivate. You will activate your environment, and then you will just concretize and install it. That's it. If you were to run this manually, you will have to concretize. But if you already proved that the package kind of compiles and you submit the log file, you don't have to concretize. You will just install the new package. And then what ties everything together, I don't know, do I have time? Okay, I have minutes, so let's go ahead. So what ties everything together is the LMOD part, which basically has different levels of development. So basically, it is interactive. It responds to the user. So we do have the entire module layout responding. So if you change compilers, if you change programming environment, the modules are going to just automatically change to whatever you have loaded. But this automatically, dynamically changes in the module path basically breaks the spider functionality in LMOD. So we have to develop a new spider functionality as well that will react to these dynamically paths. And finally, we also add into LMOD an HTTP API endpoint to log module usage. And then I have more details, but if you're interested, I will be around. And I will be super happy if I had to put this because they asked me. If you are interested in joining, please go. Okay? Thank you very much.
Thank you.